All right, good morning, guys. I hope everybody's doing well. And I hope you had a great weekend. Does anybody have any questions, comments, problems before we get started on new material?
Yeah, do we have a lecture quiz on Wednesday before the exam?
No,
Okay.
there's not one on Wednesday. Anything else? So as far as exam goes, like I said, I will be in the WebEx in case anybody has any last minute questions that they want to ask or anything like that. I will be available between 8 and 10, just like normal. And actually, I have office hours on Wednesday, so 8 and 11. So if there's anything that comes up that you want to talk about, that's fine. Like I said, I should have those graded by a week out, but I will do everything I can to have them graded by Friday. So, all right. Anything else before we get started on new stuff? Okay. So now that we've got our basis set for where we go with stoichiometry and how we set up our balanced equations, how we get the formulas that we need to be able to do that, how we set all of that up, we can move into understanding some more of those reactions that we're looking at, and then doing additional calculations with those reactions. Okay, so we're going to be talking about a couple of different reaction types today, specifically precipitation acid-base reactions. And all of these are based in aqueous solutions. So we're going to be talking about solutions in water and the behaviors that we see there. Okay. So specific topics, aqueous solutions. We'll talk about electrolytes, acids and bases, and precipitation reactions. But a little bit of review. Gold reacts with chlorine gas to create gold-3 chloride. How many grams of gold-3 chloride are formed if 1 gram of gold is reacted with 2 grams of chlorine gas? Okay, let's start at the beginning. Give myself a little more space here. I know that I'm going to be reacting gold, which is AU, and chlorine gas, which is Cl. Chlorine is one of those gases that's always diatomic, so that's a Cl2. Gold is a solid, although the states are not important to me. Alex is big on them. So, and make gold-3 chloride. Now, gold-3 chloride is made from Au3 plus and Cl minus. So when we put those together, we're going to have an AuCl3. How many grams of gold-3 chloride? So how much of this do I make? If I start with 1 gram of gold or 2 grams of Cl2. So question becomes how many grams am I going to form? Because I'm going to go to grams. It does say grams. So I will need molecular weights for both AlCl2 and AuCl2 and AuCl3. So my Au, if I find my periodic table, it's Ag, there's Au at 196.967. Cl2 is going to be 2 times 35.45. Which if I actually turn my calculator on, I might be able to calculate 70.9. And my AuCl3 is then going to be 196.967 plus 3 times that 35.5 is 303.317. Now, the other thing, I know that this is not balanced. I know that this is not balanced. And the reason that I know that is because I have 2 chlorines on the reactant side and 3 on my product side. So to take care of that, I need to make them the same number. Since I have a 3 here and a 2 here, my lowest common denominator being 6, I'm going to go 2 there, 3 there. That takes care of my chlorines. But now I messed up my gold, so I need to multiply this by 2. Okay? So that is my balanced equation. And now I have all of my molecular weights, so I should be able to do my calculations. First calculation I want to do is to take that 1 gram of AU. I need to convert it to moles first. So I will divide by the 196.967 grams per mole of AU. I know that there are 2 moles of AU, and that gives me 2 moles of AuCl3. And that 1 mole of AuCl3 is 303.317 grams. And of course, happy math on that. I end up with 1.54. Right, round to 3 sig figs. And of course, that cancels with that. My grams have canceled. My moles of gold have canceled. My moles of AuCl3 have canceled, and it leaves me with an answer in grams of AuCl3. Okay, there's that calculation. I also have to do the same calculation for my chlorine to see which is my limiting reagent. So 2 grams. Actually, oh wait, that should be that one. So that should be there. And that means that should be 1.53. Yeah, no, it's still 540 by the time we round. So 2 grams, 1 mole of Cl2, and that is 70.9 grams of Cl2 per mole. I know that 3 moles of Cl2 are required to make 2 moles of AuCl3. And I'm still going to multiply by the mass of the AuCl3, that 303.317 grams per mole of AuCl3. Moles have canceled, grams have canceled. That leaves me with an answer in grams of AuCl3. So 2.000 divided by the 70.9 times 2 divided by 3 times 303.37. And there I get 5.71. 704 grams. Obviously, the smaller of those two numbers is the 1.540. Not surprised by that. So this is my limiting reagent. That then tells me how many grams that I would actually be able to make from this combination of materials. Okay. Question about what I did there. And second question says, from the information you have, can I predict, based on, without having done that calculation, what my limiting reagent was? No, I couldn't. I mean, obviously I didn't, okay? And while I have a guess, I never know if that guess is correct unless I do the calculations. What is my limiting reagent? My limiting reagent is the gold, and I know that because it produces the least amount of product. And what is the percent yield if only 1.042 grams of gold 3 chloride is formed? Okay, so my percent yield calculation is my actual yield over my theoretical yield times 100. Now the actual yield is this right here, the 1.042 grams. That's how much I actually made. My theoretical yield is what I calculated, that 1.540 grams, and I multiply that by 100. 1.042 divided by 1.540, and that gives me 67.66%. 4 sig figs in my numbers, so 4 sig figs in my answer. Okay. Now, how much of the non-limiting reagent is left over? Well, isn't that an entertaining question? And it's one that we haven't really talked about yet. Right? But let's talk about how that looks. Now, I know that I haven't used all of the Cl2. That was present in excess, and I made way more of the gold 3 chloride using that. So I know that that's the one that's in excess. I need to know, based on the amount of gold that's present, how much Cl2 would have been used. And so I need to know, based on that 1.000 grams of Au, and then converting that to moles, what the ratio between the moles of Au and the moles of Cl2 are. So I know that it takes 2 moles of Au to react with 3 moles of Cl2. And then if I need a mass, because I start with a mass, so I need to know what that mass is, then I have to multiply by the mass of the chlorine, 70.9 grams of Cl2 per mole. Moles cancel, grams cancel. That leaves me with an answer in grams of Cl2. And this is how much mass of Cl2 I would actually need to complete this reaction. Okay, fine. And I need 0.539, which has to round to 0.5400. And of course, since it's 4 sig figs, I need to include those last 2 zeros. So once I round this, that's going to leave me with this reported answer. Now, I know that's how much I need, right? But I know that I have more than that. So if I want to know how much is left, I have to do the subtraction. So I started with 2 grams. I'm going to subtract the 0.5400 grams, and that's going to give me 1.460 grams of Cl2 that remain. So that tells me how much is left. So again, I need to calculate how much was required based on my limiting reagent, and then subtract that from the amount that I had present. So that's how much I find out, how much is left over. So any questions about that? Okay.
This may be a weird question, but in the original question, how did you get 303.317? Because for some reason, when I did my calculations, I did not get that.
So I have an AlCl3 or an AuCl3. I took the mass of the Au, which is 196.97, plus 3 times 35.45. And that gives me 303.32 is if it's 0.97, but that's a different periodic table than I use the initial time. So it's 3 times the chlorine plus the gold. That's how I got that mass.
Okay.
Anything else? Okay. All right. So now we're going to talk about aqueous solutions. Now, how do we define an aqueous solution? It's a homogeneous mixture of 2 or more substances. So I take something that is uniform in nature or character throughout. That's what homogeneous is. By contrast, a heterogeneous mixture, areas differ in nature or character. So if I were to sample from 2 different places, I might get 2 different results in terms of what I'm looking at. An example of that were fairly typical, at least that I've seen, Rocky Road ice cream. Not the same every place that I sample it. So that is something that is a heterogeneous mixture. And what I measure is going to be based on the sample that I take. A homogeneous mixture, on the other hand, is consistent throughout. So it's not going to matter where I sample it from, what I'm going to see. One of the other things we need to talk about is what is a solute? So a solute is a substance present in the smaller amount that is then dissolved in the solvent. The solvent is the substance present in the larger amount. So typically when we're talking about solutes and solvents, we talk about things like adding sodium chloride to water water is my solvent in that case, sodium chloride is my solute. But again, that is defined that way because there's more water than there is for that sodium chloride. Now, an aqueous solution, my solute initially is a liquid or solid, and the solvent is water. Okay, so it doesn't matter what my solute is, but my solvent has to be water. That's how we define an aqueous solution. Okay. Cool. Talking about stuff in water. Now, let's talk about one other thing that happens when we go into water. When we have compounds that are dissolved in water, their behavior depends on what kind of compound they are. And this gets us into the subject of electrolytes. Now, electrolytes are great things. We've all been told that Gatorade is good for us, right? And it contains electrolytes. An electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. That's where that term comes from. The reason it can conduct electricity is because it creates ions in solution, which can then move when electricity is applied. So if we have something that breaks up and becomes cations and anions, like an ionic compound, then that is going to be an electrolyte. Now, not all electrolytes are the same. Some things are good, some things are bad. So how do we know if it's a good electrolyte or a bad electrolyte? Well, that depends on what kind of solution, what kind of material it is. Most of our strong electrolytes are actually ionic compounds, okay? Things that we typically talk about, sodium chloride, sodium hydroxide, barium hydroxide, any ionic compounds, HCl, HNO3, HClO4, and H2SO4, okay? Those are things that come apart in a predictable way when we put them into solution. There are other things that we know, however, that don't necessarily come apart in predictable ways, or that come apart less than the rest of it. So if I put CH3COOH into solution, I get an electrolyte, but it's a very weak electrolyte. For the same amount of material, the same number of moles of HCl versus CH3COOH, I will have a stronger electrolyte for HCl than I do for CH3COOH. Okay. We also have non-electrolytes. So these things, when they go into solution, don't conduct electricity. All right. So that's important that we understand that some things come apart, but not so well. Some things don't come apart at all. That would be why they're non-electrolytes. Okay. And one of the reasons that things come apart is because of this weird structure for water. And I'm going to say this because water is a very weird material compared to almost everything else. So it's neutral. It is. But if I draw this structure of water, I have this big O, takes up a lot more space, two little hydrogens that are out on the ends. I know that oxygen is far more electronegative, so it wants those electrons far more than the hydrogen does. And that's because of its placement in the periodic table. If it pulls those two electrons off of the hydrogen, it becomes like the nearest noble gas. And so it wants those electrons. Those hydrogens, on the other hand, are very willing to give them up to be like, to not have any electrons, okay, to be H+. That is something that they're capable of doing and they're happy doing. Now, not only because of that electronegativity, so all of that electron density being pulled towards that central oxygen, but also because of the shape of this thing. So we have an oxygen here and two hydrogens down at this end. They are down on one side. We end up with something that's called a dipole moment. So we have a net negative on one end and a net positive on the other end. And it's called the dipole moment. We'll talk about that a lot more later. But it does contain a negative end and a positive end. Because it has that negative end and positive end, it's very favorable for it to interact with ions, right? So when something like sodium chloride goes into solution, it's been hanging out together because the sodium and the chlorine don't want to be ions on their own. They want to be neutral when they're in space, right? But when they get surrounded by the water, it's more favorable for them to interact with the water. So the Na plus is attracted to the negative end of this water, and the Cl minus is attracted to the positive end of this. Okay, and it turns out that surrounding those ions with water is favorable compared to them hanging out together. That process is called hydration. So that's what happens when we have things that are ionic that go into solution. Now, this isn't always the case. For some things, it's not as favorable for them to come apart and be surrounded by the water. And that's why some things are not great electrolytes. Okay, so some acids actually have more ability to stay together than they do to come apart. And there are lots of reasons for that, and we'll talk about a lot of that later. But some acids are considered strong acids, they completely dissociate. Some acids are considered weak acids, they don't completely dissociate. So those are behaviors that we'll need to be able to eventually look at and predict. All right. So questions about that? All right. We talk about acids and bases and strong versus weak electrolytes. Strong acids completely dissolve. That process is called ionization. So HCl, for instance, is a strong acid. So it becomes completely H plus and Cl minus. So whatever concentration of HCl I have, whatever number of moles that I put into that water, that becomes the same number of moles of H plus and the same number of moles of Cl minus. And the concentration of HCl is actually not anything. It's zero because it's completely dissociated. So it's a complete separation of the cation and the anion. And that's why this single-headed arrow is here, because that reaction only goes in the forward direction. We don't have H plus and Cl minus coming together in water to make HCl again. That does not happen. A weak electrolyte, on the other hand, is not completely ionized. That can be written with the protons that can ionize separated from the rest of the molecule. So when we talked about CH3COOH, that's a weak acid. It's actually called acetic acid, also known as the main component in vinegar. So acetic acid can lose this proton out here at the end. We end up with CH3COO minus and H plus. Now, the anion here is called the acetate ion. The acid is acetic acid. This is written with a double-headed arrow because not only does it exist as CH3COOH in water, it also exists as CH3COO minus and H plus. So both of those exist, both sides. The ratio of that depends on the strength of the acid. Okay. When that acid comes apart as fast as it comes back together, so it's falling apart at the same rate that it's coming back together, that process is called equilibrium. And so we can't, from an outside perspective, see that anything is changing anymore, unless we've done some really fancy things so that we can label things and see that they're actually changing. Okay, but that's what we call equilibrium. So that's the difference between our strong and our weak. So things that are strong electrolytes have completely dissolved. Things that are weak electrolytes have not completely dissolved. Questions about that? Okay, so this brings us to our next topic, which is precipitation reactions. So definition-wise, reaction results in the formation of an insoluble product. That insoluble product crashes out of solution. We make some solid that crashes out. So these things that we formed down here at the bottom, these were not present in the initial solutions when we mixed them together, but they were made after we did the mix. Okay. That solid is called the precipitate. It's an insoluble product that's formed during the reaction. Precipitation reactions are often metathesis reactions, aka double displacement. Okay. So that means that when I'm talking, and for instance, we'll talk about sodium chloride that can react with AgNO3, so gold nitrate, and that will give me an AgCl plus an NaNO3. This is aqueous, this is a solid, this is aqueous, and this is aqueous. Okay. So anything that's aqueous is dissolved in water. That AgCl is a solid that precipitates out. And so if I mix those things together, I will get that solid. We'll talk about how we predict what those solids are going to be. There are rules for being able to do that, but that's what we're talking about. Now, this is a double displacement reaction because the cation here has replaced itself with, instead of being with this anion, it's now with the other anion. So we've changed partners. So that's a double displacement reaction. Okay. So those you should be able to write just from the starting materials. You should be able to predict your products. And then eventually you'll be able to predict which one of those is insoluble. Okay? So that's one of the things that will be done with this set of things. Now, how do we know if we're going to make an insoluble product or not? Well, that depends on the solubility of our products. The solubility is defined as the maximum amount of solute that will dissolve in a given quantity of solvent at a specific temperature. It is temperature dependent, absolutely temperature dependent. And so at a different temperature, we're going to see that solubility is different. This is something you're probably aware of, because if you've made sweet tea, us being in the South, we probably have, as that tea gets warmer, we'll see that more sugar dissolves. And that's because sugar is more soluble at higher temperature than it is at lower. Okay. Not all things go up in solubility at higher temperatures. Starch is more soluble in cold water than it is in hot water. Okay? And that's one of the reasons we can use it as a thickening agent when we heat things. Okay. So that's stuff that we can see. All right. Now, not everything has the same solubility. We're not going to talk about any of the math that goes with that. That's part of what we talk about in 111. For this part of it, we're only going to talk about the qualitative side of it, i.e., what product am I going to get? What is it going to look like? Are they going to be solids or not solids? Okay. So how do we do that? Well, you get a list of solubility rules. Now, come on, catch up. Sorry, technology's not cooperating today. There we go. So you get a list of solubility rules. Now, the solubility rules that you have for the exam handouts are slightly different than this. They're on page 6 of the exam handouts, so you will see them there. They are similar. I mean, they're based in this same list, but they're not written out in what I would say is as confusing a manner. The set of rules will determine if the salt formed or soluble. They must be applied in order. So if I'm looking at these things that I've formed, right? And when we talked about this formation before, we had an AgNO3, and we added NaCl to that. We made AgCl plus NaNO3. If I wanted to look through this, all sodium salts, potassium salts, ammonium salts are soluble. So I know that this is going to be soluble. I also know that this is going to be soluble. So both of those are going to be fine. My nitrates are also soluble. Okay, that's why this one is soluble. Okay? That's that second rule. And then we get down and it says all chloride, bromide, and iodide salts are soluble except those that contain lead, silver, or mercury. And so because this one contains silver, it is an insoluble salt. Okay? That's why it precipitates out. Okay? But again, we need to make sure that we're paying attention to the order in which these are applied. So if it's soluble by the first rule, then we don't need to look beyond that. Question about that? We'll get some practice with this, I promise. Predict if the following salts are soluble or insoluble. Would you expect them to be good electrolytes, and why? So I want you to take a minute. Hopefully you have your exam handouts, and you can take a look at the solubility rules that you have to predict whether or not these things are soluble. For me, I'm going to say, okay, this is soluble because of this ion in this rule. That's the way I tend to do this. So when I walk through this, that's what I'm going to do. I want you to look through your list and see if you can predict what the solubility of some of these things are and why you would say that. Okay? I'm going to give you a couple of minutes to do that so that you get some practice with this, because I practice. I've been doing it for a while. So I am looking here at my solubility rules, from the exam handouts that you'll have on the test. So again, this is page 5 of the exam handouts. And you'll see it says solubility rules, so hopefully we can find that. And I'm looking at sodium carbonate. All common salts of group 1 elements and ammonium are soluble. Well, group 1 is the alkali metals. Na is an alkali metal, so this is soluble. And this is rule 1 that says that. Okay, so it doesn't matter that carbonate's on it, because I can see that if I look down here, carbonate is one of those things that's often insoluble, but it does say, except for those in rule 1, right? So they have to be applied in order, so I know that it's soluble because of that group 1. Okay. K2SO4, same thing applies here. This is going to be soluble because K is a group 1 metal. Ammonium is also a group 1 metal. It's in that group, so ammonium is part of rule 1, so this is soluble. BaNO3 2. BaNO3, all common nitrates, NO3 minus. So my nitrate is there, so this is soluble based on rule 2. Okay. AgC2H3O2. All right. All common acetates are soluble. Awesome. So this is soluble as well, and that's based on rule 2. CaClO3. Again, we have our, and that should be CaClO3 too. Sorry. And our chlorates are also soluble. That's also based on rule 2. CaOH2. Okay. So let's see what we can find. I haven't found anything for group 2 metals. It says, except for those in rule 1, carbonates, hydroxides, and are insoluble. So this is an insoluble. And that's rule 5. If I look at Li2S, that is going to be soluble because lithium is an alkali metal, so he's group 1. So this is going to be soluble based on rule 1. I'm looking at Mg3PO42. Mg is an alkaline earth metal, so that first rule doesn't apply. So now I need to go look for my PO4. And if I come down here, I see phosphates are insoluble except for those in rule 1. So this is going to be insoluble. And that's based on rule 5. And my NH4CO3, again, NH4 is part of rule 1. That's going to be soluble because of that. Typically, when I'm looking at this, I almost always try and identify, is the metal going to be a problem first? Because the metals usually are the biggest problem. So I always look at the metal first. Once I've eliminated or discovered whether there is a rule specifically for that metal, either soluble or insoluble. If that fails, then I'll look at my anions. Okay, so that's how I approach that. But again, I just keep looking down the list, applying in order to see which rule applies to the compound that I'm looking at. Questions about how I did any of my predictions? So now I know if they're soluble or insoluble. How would I know if they're good electrolytes and why? Well, I will say that if they're soluble, I would expect them to be good electrolytes. Because if they're soluble, that means that everything is going into solution. That means that they're probably breaking up, and they almost always are. That should give me a good electrolyte. All of these are ionic compounds, so they have to ionize when they go into solution. So I would expect them to be good electrolytes if they're soluble. Now, if they're not soluble, they're either non-electrolytes or they could potentially be weak electrolytes. It depends on where that solubility line is for that. And again, that's one of those things that we don't really talk about. There is an arbitrary line for how much goes into solution when we call it soluble, because it's not really a very distinct line for where that happens. So it may be a weak electrolyte or it may be a non-electrolyte, and that would depend. We'd have to test it. There's no way to predict that at this point. Okay. Some of the ways that you may see this kind of thing, you may see it in terms of which one of these is not soluble. Which one of these would you expect to be soluble? Tell me from this list, are they soluble or insoluble? I might also ask the question in the way of, is it which of these are strong electrolytes? Okay, and again, the logic there should still apply. Okay. All right. Well, this brings us to our fun discussion of equations. So we talked about how to write equations a couple of lectures ago, right? And we said, okay, we're going to write this equation, we're going to balance it. That's awesome. That equation is called a molecular equation. It's called a molecular equation because everything that's shown is a molecule. Formulas are composed and written as though all species existed as molecules or whole units. Okay, so it's easy for us to identify our reagents there. When we talked about this reaction previously, we talked about our sodium chloride reacting with the silver nitrate, and that gives me that AgCl solid plus the NaNO3. Okay, this is a molecular equation because everything is shown as if it exists as a molecule. Awesome. But I also know now that anything that's in here is an aqueous component. Is not actually like that in solution. So when NaCl goes into solution, this is what happens. And so we get that Na plus and that Cl minus, both of which are aqueous. They're surrounded by the water. And so we have both of those ions existing separately. So it is possible for us to show the ionic equation where we explicitly show all of the dissolved ions. If we were to do that, we would show this for this one as Na plus, which is aqueous, plus a Cl minus, which is aqueous, plus Ag plus, which is aqueous, plus an NO3 minus, which is aqueous, going to AgCl solid, because those ions are not dissolved anymore. They've come together to form that solid, plus the Na plus, which is aqueous, plus the NO3 minus, which is aqueous. Okay, so in this case, we've explicitly shown all of the ions as separate species because I know that's how they exist in that beaker. Okay, and that's great. But the thing is, I don't always care about all of these things. And why is that? Well, because not all of these things are actually doing anything interesting. You might notice that this Na plus hasn't changed, hasn't done a damn thing. In fact, if we were to talk about this as a fight, that being right there wasn't involved in the fight, but he's watching the fight. So he's a spectator. Okay, he's just hanging around for net neutrality. Okay, now while he's important to have in that beaker, it's important that he's there. He's not part of the active chemistry. So if we're interested in the chemistry and the formation of that solid, we can talk about just the ions that are involved in making that solid. And that's when we talk about a net ionic equation. And so we would eliminate anything that isn't directly involved, i.e. the Na and the NO3. So since they haven't changed and done anything, those would be eliminated. So I can write this as Cl minus Aq plus Ag plus Aq goes to AgCl solid. And again, I am explicitly showing the formation of that solid. Now, when we talk about doing this for acid-base reactions, we'll be talking about the formation of the water to do that, okay? So that's the part that we're going to care about there. But here we're looking at anything that has changed phase. So when we talk about forming water, we've gone from an aqueous ion to forming liquid water. So same idea, all right? So these are the three types of equations that we're going to be able to deal with. Now, I mentioned when we were starting to write equations that it's important to know what those ions are to make sure that we've got them balanced correctly, right? Because I need to know what's the charge on the cation, what's the charge on the anion. And so what some people find is that it's easier to write this equation first, then form the molecules, balance the molecular equation, and then make sure that the numbers are the same in the ionic equation, okay? I don't really care how you do it. Doesn't really matter to me. Just make sure that your charges match up the way that they should. So all of these are +1 and -1, so that's great, but it's not always that case, right? So any questions about what we're talking about so far? So let's talk about some molecular equations. So I have a couple of different examples here, things that we've talked about, and the NaCl is right here because it's the easy one for me to remember. But this is a bunch of different molecular equations. So PbNO3, 2 plus 2Ki goes to PbI2 plus 2KNO3. And of course, since I have two I's on my product side and the PbI2, which I need because Pb is 2 plus, so I need 2I minus, that means I need 2Ki's on my reactant side to make that balance. And of course, once I do that, then I need to have 2 Ks and 2 NO3s on my product side to make that balance. So that is a balanced molecular equation. Now, no ions are shown there. Everything is shown as a compound, so that's a molecular equation. We can also have MgCl2. Mg is an alkaline earth metal, so he is a 2 plus. Therefore, I need to have 2 Cl minuses to go with him. Ag is a plus, NO3 is a minus, so that's AgNO3. And that gives me my MgNO3 as a product. Right? We talked about the NaCl, so I'm not going to berate that one again. BaCl2, again, Ba is an alkaline earth metal, so he's a 2 plus. Therefore, I need 2 Cl's to go with him. That's why I have those two. And then we have Na2SO4. Now, SO4 is a 2 minus, so if I need 2 Na pluses to go with that, then when that Ba goes with the SO4, when this guy right here goes with this guy right here, they're both 2s. So it's a +2 and -2. So we end up with a BaSO4. Then we end up with 2 NaCl's because I had 2 Na's here and 2 Cl's there. Okay. We can also talk about HCl, which is hydrochloric acid, plus NaOH, sodium hydroxide, reacting to give me sodium chloride and water. Okay, so this is an acid-base reaction. We'll talk about the details of those in a little bit, but I wanted to present one here. So I have my acid, it reacts with my base, that gives me a salt. This happens to be table salt and water. It's always an ionic compound in water that I get from an acid-base reaction. Okay, so those are the molecular equations that go with these processes. We'll see what happens when it gets a little more complicated. So now we can talk about the ionic equations, because that's always the one that we do next. So when we do that, we show each species with its charge. So it's a Pb2 plus, that's aqueous. I have 2 NO3 minus, because when that Pb NO3 2 comes apart, I get a Pb2 plus 2 NO3 minus. The reason that it's a 2 here is because of the charge. That just means that there are 2 of them present. So when they come apart, I get 2 of them. Okay? I have 2K plus 2I minus, and that gives me my solid PbI2 plus 2K plus 2NO3. Okay. We have our Mg2 plus 2 Cl minus. Again, same reasoning here. I have 2 Ag plus 2 NO3 minus. It gives me 2 AgCl plus Mg2 plus 2 NO3 minus. And again, we have to have 1 Mg on both sides, so I have to have those 2 NO3s there. So that's where that comes in. Okay. Our NaCl we've talked about previously. We have our Na plus, our Cl minus, reacts with an Ag plus an NO3 minus to give our AgCl solid, plus the Na and the NO3. Okay. Ba2 plus here, plus 2 Cl minus, goes to plus 2 Na plus the SO4 2 minus, gives me that BaSO4 plus 2 Na plus 2 Cl minus. And HCl, H plus Cl minus plus the Na plus the OH minus gives me an Na plus and a Cl minus and H2O as a liquid. Okay. So those are my ionic equations. They're longer. It takes more space to write all of that out, but those are our ionic equations. If we want to move to our net ionic, we have to remove anything that just stood around and didn't participate. So looking at these reactions, I know that my solid is made from the Pb and the I. That means that this is a spectator and this is a spectator. So those will go away when we get to the net ionic. When we make our solid down here, AgCl, so we'll get rid of the Mg2 plus, and we'll get rid of the NO3 minus. We make our solid down here. That is our AgCl again. We made that again. So we get rid of our Na plus and our NO3 minus. We make our solid of BaSO4. And so I'll get rid of my chlorine and I'll get rid of the Na because that was someone involved. And when I talk about this one, I make this H2O. The H is part of that. The Na is not. The Cl is not. So those are my spectators there. And the only things that are part of this are the H plus and the OH minus going to the H2O. Okay. So those are my spectators. So I would expect that all of those things are going to go away when I talk about those net ionic equations, which shockingly we're going to do here. So my net ionic equations, I've gotten rid of all of those spectators. Okay. We have Pb2 plus 2I minus goes to PbI2, solid. Cl minus plus Ag plus goes to AgCl. Now, this net ionic equation, a note on that. When we had this balanced previously, we had 2 Cls and 2 Ags to make 2 AgCls. And that's because of the balancing with other things, specifically this Mg2 plus. If we're talking about the net ionic equation, those 2's are not required. Since there are 2's in front of all of them, I can get rid of them. And that means that the net ionic equation for both of those reactions is exactly the same. And it should be, because I made AgCl in both cases. So they should be the same net ionic equation, right? When we talk about our Ba and SO4, we have Ba2 plus SO4 2 minus to give me BaSO4 solid. And then H plus the OH minus going to the H2O. Okay. So only the ions on the reactant side appear that make those solids. Those are the only things that we care about. Okay. Now, I have a tendency to try and write these as the cation first, the anion second, and that's because I know that on this side it's going to be cation first, anion second. That is not required, absolutely not required. You'll see that here. I have Cl minus and then Ag plus. It is not required that we do that. It's just a convention that that I have picked up when I think about it in my own head. Doesn't matter how you write it. Okay. So practice. We absolutely need practice. So I want you to write molecular, ionic, and net ionic equations for the following things. Now I'm going to give you some time to do this, and then I'm going to walk through what I would have written for the molecular for all of them. I will walk through what I would have written for the ionic for most of them, and I will for some of them, and I will definitely go through what I would have written for the net ionic for all of them. Okay, but we'll pick and choose. I'm not going to write all 3 for all of them just because it takes forever. So if there are any that you particularly want me to do, let me know. But I want you guys to practice with this for a little bit before I do it. Okay. Okay. Well, I don't want to torture everybody forever. So I'm going to start talking about what the approach that I take is to doing this. And I've written a bunch of steps up here at the top. So it's a symbol, charge, molecules, balance, solubility, ionic, spectator, and net ionic. So in order to do this, to convert from the wording that I'm given to the formulas, I need to know what those symbols are. So that's the first thing I did. I went through and identified all of the symbols for the things that they gave me. Anything that was listed as one of those common polyatomic ions, I know what that charge is, so I included it here. So acetates, C2H3O2 minus is an acetate, so he's a minus there. I have nitrates, NO3 minus, and that's right here, NO3 minus. Okay. So that's how I know that. The SO4 2 minus, I know because this is H2SO4, and if there are two H's, then there must be a 2 minus on the SO4. Now I also see that SO4 is, okay, maybe not. Oh, there he is, SO4 2 minus. Awesome. So anything that's a polyatomic, I know exactly what its charge is. So that takes care of those first two steps. When we talk about the rest of them, I need to make sure that I know what those charges are so that I can balance those formulas correctly. Copper 2 bromide is not so complicated. And the reason for that, bromine is a halogen. So let me pull over my periodic table. So bromine is a halogen. He wants to pick up one electron to be like the nearest noble gas. So he's a Br minus. When we talk about copper 2, I can look for him, okay? And Cu is right here. But since he's in the D block, I know he can have multiple charges. The charge is given by this Roman numeral. So right here, it says copper 2. So he's a 2 plus. Okay. When I talk about silver, he is also in the D block, but I know that I have a silver 1. So that's an Ag plus. So this is, again, copper 2 plus and a silver 1, and bromine is still minus. Goes. When I talk about mercury 1 is a weird one. Now, mercury 1 is written right here. It's one of the solubility rule things. And this is Hg2 2 plus. Mercury 1 always exists as a dimer, so it always exists as Hg2, but it's also a 2 plus. So that's where I got this formula that I've written right here, that Hg2 2 plus. Okay. Nitrate is NO3 minus. My potassium, again, he's an alkaline metal, so he's going to be a +1. And my iodine, again, halogen, he's going to be a -1. So that's how I have charges for those. Potassium K, NO3 minus. We talk about our barium. Barium is right here. He's an alkaline earth metal, so he's going to lose 2 electrons to become a Ba2 plus. 2 plus there. And my hydroxide is listed as an OH minus. And I know that that's an OH minus because I work with it all the time. It's also listed right here as a hydroxide OH minus. So it's in the list of common polyatomic ions as well. As long as I need to deal with this solubility stuff, I might as well look and see if it's here. Okay. Sulfuric acid, we've got water, H2O, and notice I listed H2O as a liquid to remind myself that it's going to change phase. Sodium, Na, and a +1. S is right here, so he's going to pick up 2 electrons to be like the nearest noble gas, so he's a 2 minus. And when we talk about rubidium, he is right here, so he's a +1 as well. And we talked about it as a plus. And fluorine over here is a -1 because he's going to pick up 1 to be like the nearest noble gas. And strontium being right here, is going to be a 2+. So I now have charges for everything that I have listed as something that I need to work with. So now that I have charges for those things, I should be able to write the molecular formulas. Okay, so copper 1 bromide, I have a Cu2+ and a Br-. That's going to give me a CuBr2. It's an aqueous component because that's what I'm dealing with. I'm going to react that with that Ag C2H3O2. There's +1 and -1 on that. That's aqueous as well. That's going to give me a Cu2+, and it's a copper acetate. So it's a CuC2H3O2. Since it's a 1- and a 2+, I have to have 2 of those acetates, and a silver 1 bromide. And notice I haven't written the phase on either of these. So it's an AgBr. Now I haven't written the phase on either of those. Now that I'm done writing the molecular portion of this equation, I can look in my solubility rules and say, okay, what do I have? So neither one of these is a rule 1. I don't see any group 1 elements or ammonium. I see all common acetates are soluble. So that means that this guy right here is soluble. He's an AQ. I then have to look and see chlorides, bromides, and iodides are soluble except silver. So this is a solid. Now, word of warning, you will find on the practice and sometimes on the test, you will be asked which of these forms a precipitate. Not all of them do. So not all of these reactions are going to create something that is insoluble. So make sure that you're actually checking everything to make sure that it's either soluble or not soluble. All right. Just because you found one that's soluble doesn't mean that the other one is automatically going to be insoluble. So make sure that you've checked that. So that's my molecular for that. Now, if I want to talk about my ionic, I'm going to do it with the ions that I've already written, right? So it's going to be my Cu2+, that's an aqueous, plus the 2 Br- aqueous, and of course it's 2 of them because I had to have 2 of them to balance here. So there are 2. I add that to that Ag+, it's aqueous. And is this actually balanced? So that should be 2 right there. I need 2 there, and I need 2 there. And that's again because this copper 2+. So I need to make sure that I've got my 2s out there. Okay, so that means I need a 2 out in front of this Ag because it's out in front of this one. That means I need 2 C2H3O2-. And of course, that does remind me that we should make sure that we've balanced it in addition to finding what is soluble and insoluble, because I kind of skipped that. This is my AQ as well. Now, that's going to give me 2 soluble guys. So Cu2+ is soluble, plus C2H3O2. There are 2 of those. They're negative, and that's aqueous. Plus that 2 AgBr solid. Okay. Identifying our spectator ions. So what doesn't make that solid? Well, the solid's made by the Ag and the Br. So copper is a spectator, acetate is a spectator, copper, acetate. And so if I look at my net ionic equation for this, I can either write this as 2 Br- plus 2 Ag plus, give me 2 AgBr solid, because that's just copying everything I have written down. So that's perfectly okay. But we also know that since all of these are 2s, I can take those 2s out. And so if I see this without the 2s in front of it, that is acceptable too. Okay, either one of those is fine. Questions, comments, problems on that? Okay. As far as my second one, I have my mercury one, which is the Hg2 2+. Since it's an Hg2 2+, and it's with a nitrate, we're going to end with that Hg2. It stays 2 down there. And then I have 2 nitrates that I need to balance that. So that looks like that. An Hg2 and O3 2. That's a mercury one nitrate. Okay, that reacts with potassium bromide, potassium iodide. Okay, and that's going to give me a mercury 1 iodide, Hg2I2 plus K and O3. And of course, since I have 2 I's there, I need to have 2 I's there. And that means that I need to have 2 there because I need to have the 2 NO3s to balance the 2 that are over here and the 2 and the 2K. Okay, so that's down. Now, in terms of what is soluble, I know that everything I started with is soluble. My mercury 1 iodide is one of my insoluble exceptions. So most chlorides, bromides, and iodides are soluble except mercury 1. So this is my solid right here. And then KNO3. Now, KNO3, K is a group 1 element, so that is soluble. Thank you. All right. If I were to write a net ionic equation for that one, and I'm looking at the formation of the Hg2 2+, Hg2I2, I need my Hg2 2+, yes, plus the 2I minus, this, Hg2I2. So that's my net ionic. I've gotten rid of everything that was just hanging out. Now, I did not write the ionic there, so if you have any questions about that, that's fine. Just let me know. Let's talk about barium hydroxide and sulfuric acid. Now, barium hydroxide, sulfuric acid, this is an acid-base reaction. It gives me water and barium sulfate. So barium sulfate is a salt. When I have Ba2+ and the OH minus, that gives me BaOH2. That's aqueous. And I'm going to react that with the sulfuric acid, the H2SO4 aqueous. That's going to give me H2O liquid plus BaSO4, because Ba is 2+, SO4 is 2-, so that's that right there. Now, I know that in order for this to work, I have to have 2 H's and 2 OH's. So that means I need 2 H2O's. That's how I can get my correct number of hydrogens and oxygens. And the way that I look at that, I always look at this as H being an H and an OH put together. So that's how I know I need 2 of each of them to make that work. So that's my equation there. And my BaSO4, actually, I believe, is insoluble. See, and this is why this is fun. So all sulfates are soluble except Ba. So this is insoluble. So we could have 2 different equations that we could write for a net ionic equation here. So depends on what we're looking at, which chemistry we're interested in. Since this is an acid-base reaction, we're often only interested in the H+. Plus the OH minus going to the H2O. But we could instead be concerned about the formation of the solid, in which case we're looking at the Ba2+ plus the SO4 2- going to BaSO4 solid. Of course, these are groups as well. Okay. So questions about that? Either one of them could be the one that I'm looking for. in the event that you're given something like this, you would be told which one we wanted if I wanted you to write an anion. Okay. And I'm going to pick on the last one. This sodium fluoride reacts with strontium nitrate. Sodium fluoride is an NaF. It reacts with a strontium nitrate, SR, and then NO3, 2, because it's an SR2 plus. That's going to give me an NaNO3, so sodium nitrate, and strontium fluoride, SRF2. So if I need two Fs, I need to have two there. That means I need to have two here because there's two nitrates and two nitrates, so that works. As far as solubility goes, I am assuming, and I can assume, that this is aqueous. This is aqueous because of rule 1, so it's a group 1 metal. My second one, all nitrates are soluble, so this is aqueous. As far as NaNO3 goes, it's a group 1 metal, so this is going to be aqueous. SRF2 is not listed here. So guess what? This is actually soluble as well. And so the question becomes, and this is the question I always get, well, if they're all soluble, then what's the net ionic equation? There isn't one. There is no reaction that happens here. So this would be listed as no reaction, and there would be no net ionic equation that you would need to show there. Now, we might ask you what the ionic equation is. And of course, I know that the ionic equation for this be 2Na plus, and I'm going to leave the states off just because I don't have a lot of space. 2F minus plus SR2 plus 2NO3 minus to give me 2Na plus 2NO3 minus plus SR2 plus 2F minus. And again, all of them are still ions, so there is no spectators that I can take out of that. Therefore, there was no reaction that occurred. Okay. So we do get things like that where there's no reaction. We do get things where there's more than one thing that we could be looking at in terms of an analytic equation. So make sure that you're aware of both of those situations. Questions about what we've done? Now, in order for us to talk about acid base, we need to talk a little bit about what an acid is and what a base is. Okay. And we're going to be talking a lot about acids and bases in the labs. You're going to do a set of titrations where you do a standardization and then a reaction between sodium chloride and hydrochloric acid. It's an acid-base reaction. It's a very common thing for us to do. Acids are sour in taste, so acetic acid, vinegar is a good example. They change colors of plant dyes, so if I dump some acid onto something that has indigo dye in it, then the indigo is going to disappear. They react with some metals to make hydrogen gas. They react with carbonates and bicarbonates to make carbon dioxide. And they do conduct electricity. Okay, so they are electrolytes because they're at least partially ionized. Bases have a bitter taste. They feel slippery like soap. Soap is typically made to feel like lye. Lye is sodium hydroxide. And that used to be the only soap that we used. And so most soaps are made to feel like that because that's the feeling we've come to associate with it. Okay. It does still change the color of plant dyes, so that's not very interesting because both an acid and a base will do that. And aqueous-based solutions conduct electricity as well. So yay, that's helpful. But those are some of the things that we talk about. Now, there are a couple of definitions that we can use to talk about the acids and the bases. So there was this guy, his name was Arrhenius, okay? And he said that acids produce H plus and bases produce OH minus. Okay? Now, that works to a point. So HCl, we talked about HCl, that gives me an H plus and a Cl minus. So this is an acid. Okay, awesome. NaOH gives me an Na plus an OH minus. So that's a base. based on that definition because I get this OH minus. But that's not the whole story. One of the most common bases that we talk about is ammonia. And ammonia, remember, is NH3. NH3, when it goes into solution, isn't going to produce an OH minus. So how does that even work? Well, that's a really good question. And that's what we need to expand that definition. So there's this guy, Bronsted. He came along and he said, okay, we need to talk about this in slightly different ways. We need to talk about acids being proton donors. So they still donate protons. So we're still talking about the exact same acid definition. But we need to change our base definition to make them proton acceptors. Right, how does that work? Well, if I'm talking about NH3 being a proton acceptor, it's typically in water. So if I react H2O with NH3, I end up with an NH4 plus and an OH minus. So we still get that OH minus, okay? But it's not directly coming from the NH3. We're still getting it, but it's not because it was donated by that species. And so this is why that Bronsted definition is slightly larger than what we talked about before. Okay, we have a lot of nitrogen compounds that are able to do this kind of stuff. They can accept a proton from places and then can act as bases in that fashion. All right. So it doesn't change the acid definition at all. It just changes our base definition a little bit. So one other thing that we need to talk about when we talk about this part of it, H plus, I have said, and I said right here, H plus goes to become H plus and Cl minus. Technically speaking, H plus does not exist in solution. It's not real. What we see in solution is actually this H3O plus, which is called a hydronium ion. But chemists are lazy. We're really lazy. And when we know that there's a water associated with that proton, we really aren't often that interested in the fact that it's associated with a water. So we show this as just going to the H plus and assume that people know the difference, that and i.e. that there is no difference. We assume that people know that H plus is the same as that hydronium. Okay? So understand that you may see both H plus and H3O plus. Neither one of them is wrong. They're perfectly acceptable to write them that way, because I mean, I would love to tell you that we all do it the way that we're supposed to do it, but we don't. And you can see that I don't, because that's not always where we're focused. Okay. So it's common to do it either way. So entirely up to you how you manage that. Okay. When we talk about definitions for protic acids, hydrogen ion donation can also be called proton donation. So H plus is a proton. So it's a description of protic acids. That's where we get this protic acid business from. There's one H plus, the acid can donate. Then it's monoprotic, one proton. HCl, HBr, HNO3, and CH3COOH acids all contain only one H that can be removed for donation. So even though there are other protons here, those cannot be donated. There are reasons for that. Reasons we're really not going to talk about. But we know that there's only one that we can give. Right? Diprotic means that two H's can be donated. So H2SO4, we have these two H's out here. I donate one of them to become HSO4 minus. That HSO4 minus can donate that H plus to become SO4 minus. That's how I get that sulfate ion. All right, so that's a diprotic. We also have a triprotic that we often talk about. Triprotic acid has 3 protons. H3PO4 can donate 1 proton to become H plus and H2PO4 minus. That H2PO4 minus can donate an H plus to become HPO4 minus. And then that HPO4 minus can donate an H plus to become PO4 minus. Okay, so that's what we mean by protic acids: monoprotic, diprotic, triprotic. Polyprotic just means more than one. Anything 2 still qualifies. Okay, so that's our terminology with protic acids. Now, the Bronsted bases accept a proton. They do not necessarily produce OH directly. Okay, so NaOH produces that OH minus, And of course, that OH minus plus CH2O can make an H2O. The NH3 takes a proton from water to become NH4 plus OH minus. So the accepting of the proton from solution is why they are defined as a base. It's because of that ability for that OH minus to pick up a proton here. And here is the ability of the NH3 to take the proton to generate the OH minus. Okay. Since NaOH completely reacts, this is not a reversible reaction. Notice we have the single-headed arrow. NaOH is only Na plus and OH minus in solution. So if I know the concentration of this, I will know the concentration of Na plus and OH minus. We'll need to be able to talk about it. Okay. Only some NH3 reacts. So this is not a complete reaction, hence why it has a double-headed arrow. It's a reversible reaction and a weak base. And indicates that the reaction can go both directions and is only partial. Questions, comments, problems about that? Okay. Acid-base neutralization. So I mentioned that acids and bases can react. When they do, they give me water, H2O liquid, and a salt, typically an ionic compound. HCl plus NaOH gives me NaCl, which is table salt. So it's a salt. Anything that's defined as an ionic compound when it's solid is called a salt. So anything that has charges when it comes apart, that's a salt. Okay. We can take our molecular equation, break it down into an ionic. H plus Cl minus plus Na plus OH minus goes to Na plus Cl minus plus H2O liquid. And of course, the Na and the Cl are both spectators, so they haven't done anything. So those will go away and leave us with our net ionic equation of the H plus the OH minus going to give me H2O. Now, if I have equal molar amounts of acid and base, so I have the same number of moles of H plus as I have OH minus, then at the end, I would have water and salt. There's nothing else left. There's no acid or base left. It's called neutralization. So we've gotten rid of those acidic properties. We've gotten rid of those basic properties, and it's now neutral. Okay. Not all neutralization reactions are complete, but they all involve turning an acid and a base into water and salt. Even if they aren't complete, I have made some water and some salt in that process. Okay. So some balancing practice for acid-base reactions. Molecular, ionic, and net ionic equations for these. We've done one version of these previously, but I want to see how you handle the rest of them. So I'll give you a couple of minutes to work on that. Okay. So for this first one, I took and I did my ionic. So I said, okay, KOH, I know is going to be a K plus and an OH minus. HBr is going to be an H plus and a Br minus. I know that I'm going to make an H2O liquid, and then I'm going to have a K plus and a Br minus. Now, K is always soluble. He's a group 1 metal. Br is always soluble unless he's with some other things, which he's not here. So those are my spectator ions, my K and my Br, and then my OH minus plus my H plus goes to H2O liquid. Now this is the only time I'm going to write that ionic equation because it's the same for all of these. Okay? I know that that's a 1-to-1 ratio because I have one OH here and I have one H here. So that's a 1-to-1 relationship. I make one water out of this thing. That's not always true. And you'll see that I've written more than one water for a lot of these. Here I have two OH minus. So that means I need two H's to go with them, and that gives me two H2O. And of course that balances because I have to have a BaI2. So I need two I's to go with that Ba. When we talk about this one right here, I have one OH, but I have two protons. So I need to make two waters from this. And so that means I need two of those to make that happen. Okay? And that makes sense because I have an Na2SO4 that would be generated over here. Okay, because SO4 is 2 minus. So I need two NAs. When I look at this one, I know that I have three H's that are here. So I need three OH's to make three H2O. And of course, that means that I end up with a K3PO4. Okay, so I need to have the same number of OH as I have H. So there needs to be parity there. I have one H here, and I have one OH here, so I end up with an H2O plus KNO3. Okay, so that's how I know how to balance those. And again, looking at how many protons I have and how many hydroxides I have, that tells me how many waters I make. And then everything else should balance based on that. Okay, so if I need two hydroxides to make two waters, I need to make sure that I've multiplied that base by 2. Okay, so that's that. Now, like I said, I'm not going to do any of the ionic or net ionic equations at this point. If you want to see them, I'm happy to hang out and talk through all of them as we go forward. If anybody has any questions right now, let me know, because if you have a question, chances are somebody else does. Okay. All right. What else are we going to talk about? Well, we're going to talk about weak acids and strong bases. All right. So I can react a weak acid with a strong base. If I take one weak acid, and notice that I've listed some strong acids and strong bases here. If it's in, and here's the way this works. If it's in this list, it's a strong acid or a strong base. If it's not in this list, and it's an acid, it has a proton that it can donate, then it's a weak acid. If it's not in this list and it's a base, I could pick up a proton from somewhere, then I'm weak base. Now, there are tables of some of the common ones that we talk about. So weak bases, weak acids, and here you'll see some of your polyprotic acids. So that's what that polyprotic means. So H2SO4, and you'll see both ionizations for that. H3 of PO4, and the 3 ionizations for that are down here. Okay, so not all of them are going to explicitly be shown. Now, when we talk about HCN, that is listed here as a weak acid. HCN is hydrocyanic acid. Right? We react that with NaOH. That's going to give me an Na plus and a CN minus, and then H2O. That's our molecular equation. Our ionic equation, H plus, CN minus from here. Na plus and OH minus from here is being Na plus and a CN minus plus the H2O. And so my net ionic equation, yet again, is still H plus plus OH minus goes to H2O, liquid. Now, this HCN, when it's present, if there's enough NaOH, will go all the way forward to produce Na plus and CN minus. That's true. That will happen. But the thing is, because this is not a strong acid, this CN minus can react with water. Okay, So what happens is that CN minus finds an H2O and it says, hey, I like your proton, give me that. And it takes it to give me that HCN back. And so we end up with OH minus. And so when we have a weak acid and a strong base, instead of being neutralized, okay, we end up with a slightly basic solution. So basic, more OH than H minus, or H plus, sorry. And we haven't talked about that part yet, but we will at the end of the term. Okay, so that's something that we have to deal with there. And one of the other things that we need to be able to deal with is that carbonates, bicarbonates, sulfates, and sulfides react with acids from gaseous products. This is mentioned because it's something that happens in the laboratory. We do a reaction that produces gas. We collect that gas to see what the state of that reaction is. Now, you guys don't do that for the virtual lab, but it is something that we need to be able to talk about because it may be on the file. So, hey, I am not going to expect you to balance one of these equations. Okay, now this is a double displacement. It produces the NaCl and the H2CO3. But that H2CO3 spontaneously decomposes to give me H2O and CO2. I do not expect that you can show me all of those products based on that. The CO3 2 minus, the S2 minus, the SO3 2 minus work exactly the same way to give us those gases. So those are present. Again, I am not going to ask you to balance one of those equations. I might tell you that Na2CO3 and HCl react to produce NaCl, H2O, and CO2. But then I've given you all three products. So that's different than asking you to predict those products. Okay? And that you might be able to ask, might get asked to balance, specifically in the form of a possible getting points back type of situation. So any questions, comments, problems about what we did today? So what are the things that you need to take away from what we talked about today? Acids can donate H+. Bases can either accept H+ or donate OH-. Strong acids, strong bases are listed on the table in the exam handout. If it's not strong, it's weak. If it's weak, it can react with water to form the protonated acid again, thus producing OH- and raising the pH. Weak bases can donate the proton to water as well, thus lowering the pH. So it depends on which one we have, weak base, weak acid. Some clear solutions, when mixed, produce a solid that is said to be insoluble. And insoluble products are something that we can predict using the solubility. So, practice, yes, lots of it. Again, things that I would expect is that you can predict the products from a double displacement reaction. Tell me if one of those products is, if all those products are soluble or not soluble. I would expect that you can balance an acid-base reaction to give me water and salt, and look to see if that salt that's produced is soluble. Okay. Once you've written that molecular equation, you should also be able to write the ionic and the non-ionic equations, and you need to make sure that you've balanced everything appropriately. Okay. So, questions, comments, problems at this point? And remember, this material will not be on the test. This is test 2 material. But that does give you a couple of days to be ready for that test. If you have anything you want to talk to me about with the test, since we are now done with the material, then we can open up the floor to anything to talk about for the test. As always, I will have office hours right after class today, so I'm available up until 11 today. If you want to meet with me after that, that is fine. We can manage that. I have office hours almost all day tomorrow. I normally take a lunch break, but if anybody wants to talk during lunch, I can make that happen. So I will be available up until 3 p.m. tomorrow. If you have questions that you want to talk to me about before you take the test on Wednesday, I will be available in WebEx so that you can do that. And as long as you get the test started before 10 o'clock, then you should be fine as far as taking it. It is a 2-hour enforced time limit, so you will only have 2 hours to work on it. It should be enough time for you. It shouldn't be a problem. I will make a post about how many questions are on there because at the moment I can't remember. I didn't look. Sorry. But I will make a post about how many questions there are going to be and how many parts that may be because some of them have multiple parts. So just so you know. And again, if you've done the exam review, you should be fine. Okay. Well, that's all I've got for you today, unless you have questions. Good luck getting ready for the test, and I will talk to you on Wednesday.
Hello.
Hi.
Did you see the chat that I sent you?
Actually, I did not get a chance to see it. I know it came through, but I didn't get a chance.
Oh,
But you're
okay.
still having problems with the respondus?
Yeah, so actually the guy at the help desk called me at like 7:45 this morning
Right.
and apparently so he knows what the issue is now.
Okay.
It's because my computer I'm using a MacBook and I updated it, but apparently every time Apple comes out with a new update, the Respondus company has to update the lockdown browser to be compatible with it.
Correct.
So then he walked me through how to take the new update off my computer, but it messed up my computer. So now I've got an appointment at the Apple store later today to fix it. So I should be good to go.
Okay. Let's chat offline because if that doesn't work and you need help getting into the test, again, I can make exceptions for the Respondus browser lockdown if we need to do that.
Okay. Um, and he gave me a ticket number that I sent to you in the chat in case you needed that for anything.
I'm good. I'm
Uh,
good.
and I
I,
can
I
email
know
that
how to
to you if
follow
you
up with
need
them
it.
if I have to.
But yeah, so I set up an appointment to go downtown to the Apple store so they can help me get the update off of my computer. And then he said after that I should have no problem whatsoever with the lockdown browser because the problems started happening right when I updated my computer. So it all
Oh,
makes sense.
well, and sadly, this is the way that it works. And sometimes, I mean, it happens for both Windows and the Mac OS, but typically with Respondus, they have a better relationship with Windows than they do with Mac. So they don't
Hmm.
always know ahead of time that something's coming. So,
Hmm.
and I can go ahead and take off the requirement for the lockdown browser for you today. So again, so you can take the quiz.
Okay, yeah, that'd be great because I wasn't able to take the Lecture 7 quiz.
Yes, and I can take care of that for you because that's not your fault. So I will do that.
And thank you for being so understanding with this. I know now it all makes sense why I'm having these problems, but thank you for being so understanding.
I would love to say that technology is perfect, but I know it isn't.
Well, it's great when it works, but it's terrible when it doesn't.
Yes, and that's exactly it. But yeah, I will take care of that because again, that's not your fault.
Okay, well, I'll get that taken right here when I get off the call, and then is the test going to use the lockdown browser since we're going to be on the Zoom call?
So, well, so the Zoom call is available if you need me.
Oh,
What will happen is that you'll need to close out of the Zoom call to be able to take the test.
oh, okay. So we log on to the Zoom call that morning, and then we log off when we're ready to take the test.
Yeah.
Okay.
And you only need to log in if you have questions or if you want to see if anybody else has questions, because I understand that too. I was that student. I always wanted to hear whatever and anybody else asked.
Hmm.
Um, but it's absolutely not required if you just want to take the test. That's perfectly fine too.
Okay. Okay. So would you recommend that I start the test at 8 in the morning?
That's up to you.
Okay.
And if you do run into any problems while you're taking the test, make a note of it. You can take pictures with your phone if there's anything that comes up, and send them to me after the fact. So,
Okay.
and we can deal with that. Sometimes things happen. So occasionally things don't show the way they're supposed to. Again, I would love it if technology was perfect, but it's not.
Yeah. Okay, well, thank you very much.
You're welcome. No problem.
Hey, I have a quick question. So,
Yes.
are you available like after my second class or
Yes. Yes.
okay,
I will be here.
okay, okay, thanks.
Yes. No problem.